everyone. I am Teacher Loressa and I am your physics teacher for today. Physicists learned about electricity and magnetism in the 19th century. We've already talked about one of the biggest discoveries, that electricity and currents can create magnetic. Once scientists figured that out, they wondered if the opposite was true. Could magnetic fields create or induce an electric current? Two physicists, Joseph Henry and Michael Faraday, figured out what was happening. It turns out that magnetic fields do induce electric currents, but only under certain circumstances when the magnetic field is changing with time. And this discovery had led to the invention of generators. Topic for today is regarding electromagnetic induction, which is the ability of the magnetic field to create current inside the conductor. In this case, we will identify the factors that affect the magnitude of the induced EMF and the direction of the induced current, which we call Faraday's law.
The content of our video is this one. We will first discuss the factors that affect EMF and also the direction of the magnetic field and current, and after that, we will have assessment.
When Faraday discovered that magnetic fields induce electric current, he set up a current flowing through a coil of wire that would generate magnetic fields. Then, he watched to see if that magnetic field induced the current in the second coil of wire. And it didn't. It is disappointing at first. When Faraday observed something weird when he turned on and off the current in the first coil of the wire, there is a brief spike of the current in the second coil, but only while the current is changing from off to on. A constant magnetic field will not cause any current, only a changing magnetic field will. We call this idea Faraday's law of electromagnetic induction. It says that a changing magnetic field will induce an EMF in a loop of wire. An EMF means electromagnetic force, which causes electrons to move and form a current. Faraday knew that magnetic field changes with time. It induces an EMF in a loop of wire. There are other factors that induce the EMF too. Changing the area in a loop of a wire changes the current too, and so changing the angle between the loop and magnetic field. That's because of what we call magnetic flux. Magnetic flux is essentially a measure of magnetic field running through a loop of wire, and when the field changes, that induces an EMF. There are three factors that affect the magnetic field and therefore the magnetic flux through the coil. 1. The strength of magnetic field, which we label as B. Second, the area of the loop. If the area is larger, then it will have a larger magnetic field and vice versa. Number 3, the angle theta, the angle between the magnetic field and the line perpendicular to the face of the loop. Combining all these factors, you can arrive that this is magnetic flux. If the magnetic field and the loop are perpendicular, then we will maximize magnetic flux. Hence, the magnetic flux is just times the magnetic field and the area.
Take note also that area, that area is equal to the length times the width. And we input the equation of the area to the magnetic flux. It becomes magnetic flux is equal to the strength of magnetic field times the length times the change in its width within the magnetic field. Then incorporating it to Faraday's law, wherein this is EMF, this is the magnetic flux over the change in time. Take note that the change in width over the change in time is equal to velocity. If that is the case, Faraday's law is equal to the EMF is equal to the strength of magnetic field times the length times the velocity of the loop. So what does that mean? There are three factors that affect the induced EMF. First is the strength of the magnetic field. The greater is the magnetic field, the greater is also the EMF. Number 2, the length of the wire. This is associated also with the number of coils. The more number of loops, the larger is the EMF. Number 3, the velocity of the loop. If the velocity of the wire as it moves is faster, then there is a faster change in magnetic flux. The faster is the change in magnetic flux, the larger is the EMF.
The unit of magnetic flux is Tesla meter square, or this is what we call Weber. When it comes to inducing EMF, what really matters is the flux is changing over time. If the magnetic flux decreases over time, then the EMF increases accordingly. If the magnetic flux increases over time, the EMF decreases. In equation, the EMF is the negative of the change in flux over time. This equation would work on EMF in one loop of wire. So, if you have more than one loop of wire, then you multiply the number of loops to the change in flux over change in time to derive the total EMF. Having 2 loops would double an EMF, whereas having 10 loops would be 10 times the EMF versus a single loop. Hence, Faraday's law of induction let us calculate how much EMF and therefore how much current will be induced in a loop of wire by a change in magnetic flux. But in what direction will the induced current flow? To figure that out, we use a rule called Lenz law. You know how current generates magnetic field? Lenz law says that the magnetic field generated by the induced current will be in the direction opposite the change in magnetic flux. If you know the direction of the change in magnetic flux, you can see the direction in the change in magnetic field generated by the current. Here, you could use the right-hand rule to figure out the direction of the current. To get a better feel about how to apply the Lenz law, we have 2 scenarios involving a bar magnet on a loop of wire. First, if the magnet is towards the loop, by moving the magnet closer to the loop, the magnetic field points upward, and according to Lenz's law, the magnetic field created by the induced current will oppose this, so it will point downward. Second scenario, the north pole of the magnet is again facing the wire, but this time you will move the magnet away from the loop. In this case, you are basically making the magnetic field less strongly upward and more strongly downward. So the magnetic field created by the induced current will point upward to counteract this change. Once you know the direction of the magnetic field generated by the induced current, you can figure out the direction of the current from there. This is where the right-hand rule comes. Make a stop sign from your right hand. Your thumb points to the direction of the magnetic field. The direction of your fingers are pointing to the direction of the current. So let's try it. We move the north pole of the magnet closer to the loop of wire. The generated magnetic field is pointing upward. The current will be moving clockwise along the loop. The second scenario, where we move the north pole of the magnet away from the loop. The generated magnetic field is pointing downward, so the current will be moving counterclockwise along the loop.
This is a flux simulation that we have a magnet on the left side, and then on the right side we simply have a wire hooked up to a voltmeter. So we will measure the amount of voltage. As you can see, there is no current right now. As I change the position of the magnet, I'm starting to get current. And you can see that electrons moving in the wire, and so I can increase the number of the wires. I can increase how much I am deflecting that middle, how much current I'm actually having inside the wire itself. Why is that? Now with the magnetic field lines, you can see that the field lines are changing. And as they change, you are getting a change in magnetic. So we're getting a current inside the wire. Now let's look at this generator. So in this setup, what I have is a magnet now. I can spin that magnet. I have my wire again, and I'm trying to induce the current inside that wire. Then I'm going to measure the amount that I'm going to achieve. So what happens when I start to turn on the water inside the faucet? It is changing the position of the magnet. As it changes the position of the magnet, it changes the magnetic field. You can see the magnetic field lines are changing, and so the current. What happens if I increase the speed of the water and getting more current? You can even have a light bulb connected to it. So now I'm starting to get energy. What happens is I increase the number of quarks. Now if I increase the water again, we even have more energy to be produced. So we are taking that energy of the flow of the water and actually making electric energy out of it. Now let's proceed to the assessment. Question number 1. Electromagnetic induction is taking place in this experiment. How much electricity is being produced? Let's see. The choices are negative 10 volts, 10 volts, 100 volts. And this question cannot be answered based on the image. What is your answer? Yes, the answer is 10 volts. Question number 2. The voltmeter is at 0 in this image. How would you manipulate the experiment to create electricity measured in volts? First choice, flip the magnet around the north pole, is facing out. Second, move the magnet back and forth. Third, take the magnet out. And fourth, add more coils around the paper cylinder. Answer is move the magnet back and forth. Third question. A magnet is moved in and out of the coil of wire connected to a high resistance voltmeter. The number of coils doubles. The induced voltage, what do you think is the answer? Yes, it also doubles. Next question. Which description best applies to Lenz's law? An induced current occurs when a magnet passes through a tube. Second, when a change in magnetic field occurs to a coil, the direction of current goes in the other direction to this change. Third, the direction of an induced current is such to align with the change that created it. And fourth, a magnet is a tube. It is always slowed by its magnetic field. What do you think is the answer? Yes, the answer is when a change in magnetic field occurs to a coil, the direction of current goes into the other direction to this change. Next question. How would the experimenter increase the amount of electricity being induced by this experiment? Yes, the answer is increase the number of coils. Next question. This picture shows a turbine generator used to produce electricity at a geothermal power plant. Electricity is produced by using steam to lamp. What do you think is the answer? Yes, the answer is spin the turbine generators. Next question. When a conductor is moved to cut the magnetic flux, an lamp is produced. What do you think is the answer? First, induced current is produced. Next question. Direction of deflection of the galvanometer pointer can be determined by. First, what is the answer? Yes, the answer is using Fleming's right-hand rule. Next question. Click all the factors affecting electromagnetic induction. What are the different factors? Yes, we have the strength of the magnet, the area of the coil, the speed of the movement, and the number of turns of the coil. Now for your assignment, we proceed to the crossword puzzle.
Let's pause the video and answer this crossword puzzle.